97.4, and the units are in Kelvin, and in degrees Celsius, that's equal to 97.4 degrees. So we know that water boils at 100 degrees, so we were close based on this thermodynamic calculation. Yeah, because actually, see, it turns out that delta H does vary with temperature. We're assuming it's the same. It doesn't change with temperature. Okay. And delta S actually also changes with temperature. So if we included those variations in temperature, then I think it would have done. I think we're really close to this calculation. So we do the same calculation for the dissolution of salt. You guys are tired of doing this calculation. You tired? Practice or you're tired? Or you're both? You're tired, but you need to practice. Okay, so let's do this calculation then. Let's see, so Jeff calculated delta S for this reaction to be, what you said it was 44, Jeff?
44 joules.
44 joules per mole per degree. So let's do it for delta H for this reaction. Okay, so we need to look up the delta H formation of each reactant and product.
NaCl is negative 411. Na plus is negative 39.
What was it? Minus 239?
166. CO minus is negative 167.2.
Okay, so we can do our calculation and see we're going to have minus 239.66 plus minus 167.2 and then minus 411.
So it's positive 4.14.
4.14. So when 1 mole of salt dissolves, 4.14 kilojoules of energy is absorbed. Okay, so we can plug in our numbers here. So we have delta G, 0 delta H, minus 2 delta S, so we have 0. Okay, so for delta S, if this is in kilojoules per mole, we need to convert from 44 joules per mole per degree to kilojoules, so that's going to be 0.044. So if we solve for T, so T is going to equal, let's see, 4.14 divided by 0.044, and that's equal to 94 degrees Kelvin. Or in degrees Celsius, that's going to equal minus 178 degrees Celsius. So if you don't want salt to dissolve in water, you're going to lower the temperature to minus 178 degrees Celsius. So that's cold. Yeah, so this is just above liquid nitrogen. Liquid nitrogen has a boiling point of 77 degrees Kelvin, so that's just a few degrees above the boiling point of nitrogen. Is anyone participating in the Physics Olympics this Thursday? Oh, good, because I heard there's going to be some demonstrations involving, was it dry ice or liquid nitrogen?
Yeah,
both? Okay.
Do you get extra credit for participating?
No. Is there any chemistry related to your project? I mean, you can't think of any chemistry related to your project?
My new selection for my race, that's more chemistry.
Pardon?
My glue selection.
The glue selection?
Yeah.
How's that related to
I
chemistry?
have super glue on my fingers to use acetone to get it off. So.
Did it work? But what does getting glue in your fingers have to do with the physics Olympics?
Building my bridge.
No, but what does it have to do with the competition part?
Less glue, lighter bridge.
No, what does getting glue in your fingers have to do with
The competition, hard work, dedication, persistence.
well, those are good qualities. Okay, I think we're ready to move on. Let's see. Okay, so let's talk about car engines. So we know that a car engine is a heat engine. We know that fuels produce heat. We know that fuel ideally should produce work, but sometimes it doesn't. So here's a schematic diagram of a heat engine. So in a heat engine, we see a hot reservoir, there's a cold reservoir, and there's something happening here. So what's happening in a hot reservoir of a heat engine? Okay, so in the hot reservoir, okay, so let's just, okay, so in the hot reservoir we have okay, so here's our hot reservoir. So what's happening in the hot reservoir? Yeah, there's a combustion reaction occurring. So if the combustion reaction is occurring here, what is being produced?
Heat.
Yeah, heat. So note that heat is being produced. So we'll call this QH. Okay, so heat is being produced from the hot reservoir. And in a heat engine, we want this heat to be converted into work. Okay, so this is where the work goes. Is all of the heat from the hot reservoir converted into work?
No.
Yeah, so note that only part of it is converted into work, and then the part that isn't goes into the cold reservoir. We'll call this cold C. I mean QC, this is the cold reservoir. So if we can actually write the equations, we say that QH is going to equal work plus QC. Okay, so this tells us that the heat from the hot reservoir is converted into work, and then some heat wasted. So where does the heat wasted go? In other words, where's the cold reservoir in your car engine? That's the environment. Yeah, the environment. And then, where is this work going?
To the pistons.
Okay, so that's what's happening here. So note that we have this is our car cylinder. The combustion reaction goes on here. And we want the heat to be converted into work. We want that work to be pushing on that car piston. Okay, so that's the work. Okay, so let's see. How is heat converted to work? Yeah, so we want some sort of expansion to occur. So how is the expansion occurring though? Because we know that the heat is converted into, we know that we want this heat converted into work, but how is that expansion occurring?
Is that the products here from the
Yeah, so one way we can do it is by, let's just choose a fuel. So what's the fuel that we use in our car? Yeah, so it's gasoline. Now gasoline is actually a very complex mixture, but we can say that most of it consists of C8H18. And then when the combustion reaction occurs, that reacts with oxygen. And the products of this reaction are
CO2 gas.
yeah, CO2 gas and H2O gas. This balances chemical equation. Okay, so let's see, we need 8 CO2s and 9 waters, which means that how many O2s do we need? 25? So we need 25 of these.
Oh, yeah.
And is the equation balanced?
Yes.
Are you sure?
Heat exchanger for display.
And do we need to change anything else?
16.
Okay, yes, we need to change these two then. Okay, so 16 and 18. So we know that from our calculation of work, that's based on gases. So note that we have 25 moles of gas reactants going to, let's see, 16 plus 18 is 34 moles of gas products. So we know that based on the moles of gas reactants and product, delta N is going to be, yeah, greater than 0. So we know that delta N is greater than 0, which means that delta V is greater than 0. So yeah, so note that in this equation, we should see an expansion due to the moles of gas produced relative to the moles of gas reactant we start with. Yes, that means that work is going to be less than 0. Okay, so we can use this to explain how the heat is converted into work. Now, the other thing too is we know that this reaction is exothermic, so this produces heat. So when the temperature of a gas increases, okay, so we have the temperature of a gas. And as the temperature of the gas increases, what happens to the volume of that gas? It should, yes, that means the volume should increase too. And we know that based on, yeah, so this is based on the ideal gas equation, PV equals NRT. Okay, so as the temperature increases, the volume should increase. This also tells us that we should see an expansion. Now, you said that all the heat is not converted into work. Why isn't all that heat converted into work?
Because some of the gas produced is not hitting the piston, it's hitting the walls.
Yep. Yeah, so we go take a look at this picture again. Note that if these are, ideally we want all of those product gases going in one direction. That is pushing toward the piston. But like George says, well, unfortunately, we're not going to see that happening. And that's because the motion of gases are described as moving randomly, which means that in thermodynamics terms, we can't get all of the heat to be converted into work because of, is it because of delta H or delta S? Yeah, because this is entropy. So it's this entropy, this disorder, which is why we can't get all that heat to be converted into work. So if you can figure out a way to get all those gas molecules to move in one direction, you can really increase the efficiency of an engine. Okay, what's the efficiency of an engine? So if we define efficiency as, let's see, the output divided by the input. So let's see, so what's our output in an engine? Work. Yeah, that's our work. What's the input? In terms of the energy. Heat. Yeah, the heat, so it's going to be QH or QC? QH. Yeah, QH. Okay, so we can describe this, use this formula as our efficiency. And what is the efficiency of a car engine? Does anyone know?
40%, 25%.
Yeah, it's like in the 20 to 25%. So what's mean is that only 20% of this heat is converted into work. And then later on this semester, we'll do another comparison of different types of fuel sources and look at the efficiencies of each. Okay, we'll do that a little later this semester. Okay, so we looked at this already. We looked at the source of gas in the car engine, what causes gas to expand. Let's compare these fuels. Methane, ethane, propane. Propane is used in, let's see, barbecue. If you have, like doing barbecue, today would be a good day to barbecue. Butane, use camping stoves or those lighters. C6H14 is hexane. So hexane is also a component of gasoline, C8H18, which we just looked at, octane. C2H5OH, what's the name of this compound? C2H5OH.